Hello, welcome to the lesson on section 12.2 series. In this lesson, you'll learn how to create a sequence of partial sums and use it to estimate the sum of a series, determine whether certain types of series converge or diverge, including infinite geometric series and the harmonic series. And we'll also look at some basic theorems about convergence of an infinite series, including a simple test for divergence. A series is a sequence in which the terms are being added together instead of just listed. If the sequence formed by its partial sums has a limit as n approaches infinity, then the series converges to that limit. When we speak of convergence of a series, we're saying that the sum exists and has a finite value. In my first example, I'll demonstrate how to construct the sequence of partial sums for the series 1, minus 1, plus 1, minus 1, plus 1, and so on. And then I'll use this sequence to determine whether the series converges or diverges. The first term in the sequence of partial sums is called S1, and it's just the first term of the series. The second partial sum, S2, is the sum of the first two terms. S3 is the sum of the first three terms, and S4 is the sum of the first four terms of the series. Thus, the first four terms of the sequence of partial sums are 1, 0, 1, and 0. Because this sequence diverges, the series also diverges. As we continue to add terms infinitely, the sums are alternately approaching 0 or 1, and thus not approaching a single value. In the second example, I'll rewrite the series 3/10 plus 3/100 plus 3/1000, and so on in sigma notation, and then determine whether it converges. The 3/10 to the n is called the general term of the series. You should be pretty comfortable with writing your own general terms by the end of this unit. Because of the way the general term is described here, I would need to plug in 1 for n to get the first term 3/10. So in sigma notation, this is the series from n equals 1 to infinity of 3/10 to the n. Because the general term is exponential, I can see that this forms an infinite geometric series with first term 3/10 and common ratio 1/10. So recall from your work in Algebra 2 and Pre-Calc that an infinite geometric series with first term a and common ratio r converges if the absolute value of the common ratio is less than 1, and the sum can be found by the formula a divided by 1 minus r. You'll need to recommit this formula to memory. This particular series does converge because the r value, which is 1/10, is less than 1. So the sum can be calculated by 3/10 divided by 1 minus 1/10, which simplifies to 1/3. And if you think about what this series was again, 3/10 is 0.3, 3/100 is 0.03, 3/1000 is 0.003. This would have added up to the repeating decimal 0.3 repeating, which is 1/3. Here's a quick derivation of the formula for the sum of an infinite geometric series. Let's start with a generic geometric series with first term a and common ratio r. The terms are a plus a times r plus a times r squared plus a times r cubed, and so on. I'll multiply both sides of this equation by negative r. And then add the two equations together. So on the left side, I get s minus r times s, and on the right side, everything cancels out except the first term a. Factor out the s from the left side, and then divide by 1 minus r to isolate the s. So the sum of the infinite geometric series with first term a and common ratio r is a divided by 1 minus r. Now we'll look at some basic theorems about convergence and divergence of any infinite series. First, if the infinite series with terms a sub n converges, then the limits of the terms themselves goes to 0. The contrapositive of this statement is known as the test for divergence. It states that if the limit of the terms is not equal to 0, then the infinite series diverges. It's important for you to know that the converses of each of these statements are not always true. The one that seems most counterintuitive is that if the limit of the terms of a series goes to 0, this doesn't automatically mean that the series converges. Here's a classic example of a series that diverges even though the terms converge to 0. Using the summation command on my calculator, you can find this by pressing alpha window, which is F2. I calculated partial sums for the first 100, first 1,000, and first 10,000 terms of the series 1 over n. The partial sums don't appear to converge to a specific value. Here's a visual explanation of the divergence of the harmonic series. The curve is the graph of the function y equals 1 over x, and I've drawn left endpoint rectangles with base 1 unit across and heights 1, 1/2, 1/3, 1/4, and so on. If I continue to draw left endpoint rectangles, the sum of the areas of the rectangles will be the harmonic series. 1 plus 1/2 plus 1/3 plus 1/4, and so on. From our lesson on improper integrals, we've already shown that the integral from 1 to infinity of dx over x diverges because it's of the form 1 over x to the p with p less than or equal to 1. So the sum of the areas of the rectangles is greater than the area under the curve, which is infinite. Thus, the sum of the areas of the rectangles must also be infinite. Since the sum of a series is a limit, it also follows the laws of limits. Thus, if the sums of two infinite series converge, then the sum of the two series also converges. The difference between the two series converges, and any constant multiple of a convergent series also converges. This concludes the lesson on section 12.2, series.